Welcome friends, Igor is here, and in this video we will learn how to represent linear systems using matrices. In this lesson we will define matrices and column vectors and use them to represent linear systems effectively. Let's take a closer look at the general form of a linear system. Every coefficient on the left-hand side has two indices. The first index indicates the number of the equation in which this coefficient appears, and the second index indicates which variable this coefficient multiplies. Each number on the right-hand side has a single index, which indicates the number of equation in which this number appears. Let me start deleting some symbols in this representation of the linear system. How about this? Do you still see what the linear system looks like? How about this? You see that you can still recover what the linear system looks like only by having these coefficients because they appear in specific positions in the linear system. So what we have is this rectangular array of numbers, which we're now going to call a matrix, and in fact, having such an array of the coefficients of the linear system is enough to know what the linear system is. Let's define a new term. An m by n matrix is a rectangular array of numbers with m rows and n columns. The first number in the size of the matrix indicates the number of rows in the array, and the second number in the size of the matrix indicates the number of columns in the array. We will usually use uppercase Latin letters such as A, B, C, and so on to denote matrices, and when we write a matrix as an actual rectangular array of numbers, we will use square brackets to delimit this array. We number the rows of the matrix starting from the top. So the top row is row number 1 and the bottom row is row number m. Similarly, we number the columns of the matrix starting from the left. The leftmost column is column number 1 and the rightmost column is column number n. The numbers that comprise the matrix are called the entries of the matrix, and each entry of the matrix has two indices. The first index is the number of the row in which this entry appears, and the second index is the number of the column in which the entry appears. And typically we will use lowercase Latin letters corresponding to the same letter as the matrix notation, with two indices I and j at the bottom to denote the entries of the matrix. Please keep in mind the conceptual difference between the objects you're working with. A is a matrix, which means it's a rectangular array, and Aij is one of its entries, which means it is just one number. Here is an example of a 3x4 matrix. Let's try to locate some of its entries. For example, to find the entry in position 2, 3, we need to take row number 2. Then we need to take column number 3. And the entry in position 2, 3 is the entry located at the intersection of row number 2 and column number 3. In this case, it is number -6. Next, let's locate the entry in position 3, 4. So this is row number 3, and remember we count rows from the top, so row number 3 in this case is the bottom row. Then we take column number 4 and we count columns from the left, so column number 4 is the rightmost column, and then the entry at the intersection of row number 3 and column number 4 is -2. This is the entry we're looking for. A column vector of size n is an ordered list of m numbers written vertically starting from the top. For now, the only vectors we will be working with are the column vectors, and therefore sometimes we will simply call them vectors. The column vectors will be typewritten in a bold font, usually using lowercase Latin letters from the end of the alphabet. It is difficult to reproduce boldface font in handwriting, and in this case we simply put a small arrow on top of the letter to indicate that this is a column vector. We define the entries of a column vector as the numbers that comprise that column vector. And now, for the column vectors, we use a single index to label the entries in that vector. The first entry is the entry at the top of the column vector, because all the numbers are arranged vertically from top to the bottom. Here's an example of a column vector of size 5. Its entry number 2 is the second entry from the top, and that is equal to -2. Let's define a very special column vector, which is called the 0 vector. It is a column vector, all of whose entries are equal to 0. This is a visual definition of the 0 column vector, but we can also define it more compactly by saying that every entry of that vector is equal to 0. Given a linear system, its coefficient matrix is a matrix which consists of the numbers which multiply the variables on the left-hand side. Notice how the indices of the coefficients in the linear system match our notation for the indices of the entries in the matrix. The vector of constants of a linear system is a column vector which contains the numbers from the right-hand side of the system of the equations. The solution vector is a column vector which contains the unknowns in the linear system. Given a linear system, we can write its coefficient matrix and its vector of constants, and we can use these to create a matrix representation of a linear system. For example, we have this linear system in 3 equations and 5 variables, and let's call its coefficient matrix A and its vector of constants B. And now we can refer to this linear system as a linear system with coefficient matrix A and vector of constants B. Oh, wait a minute. You're not supposed to have blank spots in the matrix, but you do have a blank spot in the linear system, so what do? We remember that whenever a variable is missing from an equation, it means it's multiplied by the coefficient 0. Therefore, this entry in the coefficient matrix is equal to 0. Remember, you cannot have any blank spots in a matrix. It has to be a full rectangular array of numbers. Now we know how to use 2 objects to represent a linear system. These 2 objects are the coefficient matrix and the vector of constants. But in fact, we can put these 2 objects together and create one single object which completely represents the linear system. And this object is called the augmented matrix of the linear system. This augmented matrix can be formed by taking the coefficient matrix and then using the vector of constants as an extra column added to the coefficient matrix. So if you have a linear system with m equations in n variables, then the augmented matrix is a matrix of size m by n plus 1. Having just this one single object, the augmented matrix, is enough to reconstruct the original system of linear equations. Also, please be careful in using the terminology. The augmented matrix is just a matrix. It is an array of numbers. It is not a linear system. As such, it does not have any solutions. You cannot solve an augmented matrix because it is simply an array of numbers. There are no equations, no equalities involved, and so there are no solutions. You can solve a linear system, but you cannot solve the augmented matrix. You can use the augmented matrices to represent linear systems. Please keep this distinction in mind. Here is an example of the augmented matrix. We have a linear system with 3 equations in 3 variables. Step number 1, we write the coefficient matrix of the linear system. But then we add one extra column to this coefficient matrix by using the vector of constants. These are the numbers from the right-hand side of the equation. And now you see that once you have this augmented matrix, you can reconstruct the original linear system. When you compare these 2 different presentations, the general form of a linear system versus the augmented matrix, it should be clear that the augmented matrix is a much more efficient way to represent a linear system. If you found this video useful, please like and subscribe to help others discover this content. In the next video in this series, we will introduce a reduced row echelon form of a matrix. I will see you later.